All right, sorry the video got cut off there. So we were talking about the limits. So we've got the limit as x approaches infinity of -1 over x, and the limit as x approaches infinity of 1 over x. Now, there are a couple of limits that we need to know. So the limit as x approaches infinity of 1 over x is equal to 0. The limit as x approaches infinity of even something of a higher power, so like say 1 over x squared is equal to 0. If we have a higher power on the top, so like let's say the limit as x approaches infinity of x squared over x, well, that's going to simplify down to the limit as x approaches infinity of x, so that's going to approach infinity. Or if, let's say we had the limit as x approaches negative infinity of x, that would be negative infinity, or the limit as x approaches negative infinity of maybe x squared, that would be positive infinity. These are basic limits involving infinity that you need to know, because we'll try to break down more complicated problems into these. The basic idea though is 1 over x. If x is approaching infinity, then we're dividing 1 by very large numbers, and that limit is going to approach 0. As we divide 1 by larger and larger numbers, the result will be smaller and smaller. Or you could remember back to the first example we looked at in this lesson. Graphically, we had that horizontal asymptote. The same thing's true if we divide by x squared. Now we're dividing 1 by even larger numbers, growing faster, so it's still going to approach 0. Now, if we have a higher power of x in the numerator than the denominator of a rational expression, then the top is growing faster than the bottom. And so we're going to have the limit approach, if we're approaching infinity, here we're approaching infinity because we just had x. But if we had something like, say, x squared and we were approaching negative infinity, then, a negative squared is going to be a positive. And then, if we have a rational expression where we have the same thing on the top and the bottom, like x squared over x squared, then that'll simplify down to 1. We can divide x squared by x squared and get 1, and the limit as x approaches infinity of 1, or any constant, is just 1. So those are going to be important for us to remember. So these both approach 0. And by the sandwich theorem, if the thing in the middle is always equal to or smaller than 1 over x, and always equal to or bigger than -1 over x, and they both squeeze down to 0, that means that this thing's limit is also 0. Okay, because this thing has to be trapped between those two functions, and we found these two functions are both approaching 0, that means the function we're interested in is also approaching 0. So there's one technique for evaluating a limit algebraically. Now, we've got a lot more properties here. They're basically all the same properties you looked at before, and we've got the same basic rules. Again, we can't evaluate the quotient if the bottom is 0, and the exponent here has to be a real number exponent. Now, one additional thing I want to add here that's missing from this table, if we have the limit of as x approaches positive or negative infinity of f times g. Or if we have the limit as x approaches positive or negative infinity of f divided by g, and we, by substitution, get one of these results. We get 0 times infinity, or infinity times 0, or we get 0 divided by 0, or infinity over infinity. These are called indeterminate forms. Which is to say, we don't know what the answer is. It's indeterminate. We're not sure what the limit is, and later in this section, we'll learn how to handle that and figure out what the limit actually is. But just be aware of that. If you get infinity over infinity, 0 over 0, 0 times infinity, infinity times 0, then we don't know what the limit is. So we would just, right now, we would write indeterminate, or once we have a couple of techniques to deal with it, then we would use those. Okay, so let's try this one. So here we've got 5x plus sine of x over x, and we're trying to take the limit as x approaches infinity. So this is the quotient rule, or the quotient property for the limits. Now we're not dividing by 0, so that's okay. And we can apply the property, but look at what happens. 5x. As x gets larger, 5x is just going to continue to get larger. That's just a line that looks like this, and it's just going to continue to increase. Plus sine of x. Well, sine of x has a very small range, right? It just varies between 1 and -1. So sine of x is going to make a very small difference. As 5x gets very large, this variance of adding 1 or minusing 1 isn't going to make a big difference. Let's say we're at 5 million. The most sine of x can add is 1, and the most it can subtract is -1. That's not going to make a huge difference. So really, the term is dominated by the 5x, and it's getting really large. On the bottom, we've got an x, and that's going to get, again, that's just a line. It's got a more shallow slope than 5x, but it's still going to go towards infinity as x goes towards infinity. So this is an indeterminate form. If we tried to take the limit on the top, we would have basically infinity plus something between -1 and 1 divided by infinity. So really it's infinity over infinity. So, and remember that we're not allowed to use the quotient rule when the limit doesn't exist. In this case, when we have a limit that is approaching infinity, that's considered not existing because it's not approaching a number. Remember, infinity is not a number. So we can't evaluate this from the top and the bottom. What we can do, though, is try to simplify or re-express. So here we could split this fraction up. And when we split it up into two terms like this, now we're going to be able to use properties of limits, because as long as both, here we're, instead of using the quotient rule, we're using the addition property, and both limits exist, right? The limit as x approaches infinity of 5 is just 5, and this was a special limit that we've been talking about, or we just talked about in the last page, which ended up being 0. So here we have that it's equal to 5. All right, let's go on to this exploration. So what we just talked about in that last example, we covered this question 1. So you might want to make sure that you understood what we were talking about and can answer that first question. I want to try to elucidate what we were talking about by doing this second question. Okay, so we've got two functions, f of x, which is sine squared x. We've got another function, g of x. which is cosine squared x. And we want to describe what's happening to these functions as we take the limit as sine squared x, as x approaches infinity. What does that look like? And what is the limit as x approaches infinity of cosine squared x? What does that look like? Okay, so let's graph one. Remember that when we're graphing trig functions, we need to be in radians, so we're going to switch into radians. We're going to put in sine, let's just clear this out, sine x, square that, and then let's do just a trig window. Let's see what this looks like. So you can see we've got a function that is varying between, it looks like 0 and 1. That would make sense, right? We'll do trace. Get back up there. Yep. So it's varying between 0 and 1. Now, would it make sense for us to say that there's a limit, that this function is approaching something as x gets very large? The function will just continue to oscillate forever as we get to larger functions, and it varies between 0 and 1. So in this case, we would say the limit does not exist for both sine and cosine because of this. And the reason is oscillation, which means that it's bouncing between two values forever. It's not, it's never going to stop. It's never going to approach a number. It's just going to keep bouncing between two numbers. So those limits don't exist. So let's consider this. What is the limit as x approaches infinity of sine squared x plus cosine squared x? Since both of these limits do not exist, we can't say that the limit of this function is one thing or another as x approaches infinity. Both the limits individually do not exist. What we can't say is that it's a number, and we also can't say that this thing doesn't exist. We just can't use the addition property at all, okay? So just because we can't use the addition property doesn't mean the limit does not exist in this case. Just like last time, if we can't use a property, we could try to re-express. In this case, sine squared plus cosine squared has a value of 1. And so the limit as x approaches infinity of 1 is equal to 1. Right? All right, let's move on. Vertical asymptotes, we were talking about that before. Now, remember we were talking about how the function 1 over x looks like this, and it has a vertical asymptote here at 0, and we would say, oh, the limit as x approaches 0 from the left of 1 over x is equal to negative infinity, and the limit, going this way, the limit as x approaches 0 from the right of 1 over x is equal to infinity. But we could have another function. We could have, like, let's say 1 over x squared that looks like this, has a vertical asymptote at 0 again, but now both limits, the limit as x approaches 0 from the right of 1 over x squared is equal to infinity, and the limit as x approaches 0 from the left of 1 over x squared is also equal to infinity. So here's an example where we could write these together as one limit. We could just say the limit as x approaches 0 of 1 over x squared equals infinity. Last thing that I wanted to talk to you guys about, which is on example 5, basically vertical asymptotes happen when you have division by 0, and you guys will want to look through these this last note.